This video is all about integrating with hyperbolic functions. I've actually split this topic into two separate videos because there's a lot of different techniques that we're going to cover that you need to know. And I think the video would probably go on a bit too long if I didn't split it up. So, first of all, let's start off with our standard results that we know. We should know these because we should always remember that whenever we've learnt anything about differentiation, like we did in the last video, we also learn about integration. So in the last video, we saw that when you differentiate Cosh, you get sinh. So that means that when you integrate sinh, you're going to get Cosh. We also saw that when you differentiate sinh, you get Cosh, which means that when you integrate Cosh, you're going to get sinh. We also saw that when you differentiate sinh, you get 1 over the square root of 1 plus x squared, which means that when you integrate 1 over the square root of 1 plus x squared, you're going to get sinh. And finally, we also saw in the last video that when you differentiate Cosh, you get 1 over the square root of x squared minus 1, which must mean that when you integrate 1 over the square root of x squared minus 1, you're going to get Cosh. Again, these results are given to you in the formula booklet, so you don't need to remember these results. I'd suggest you probably will remember the top two. You might not remember the bottom two, but you do need to be able to use them in a series of different examples. And these are, we're going to cover a range of different techniques in this video. So we're going to start off with a nice simple one. We want to integrate Cosh 4x minus 1. Now, I know that Cosh integrates to be sinh. Oops, make that a bit smaller. So I'll get sinh 4x minus 1. But by the reverse chain rule, I know I need to divide by 4. So I'll have 1/4 sinh 4x minus 1, and don't forget your plus c constant. Next, getting a little bit trickier now. We want to integrate 2 plus 5x all over the square root of x squared plus 1. Now, we've seen in the earlier topic of calculus how we can split a fraction like this up into two separate fractions, and so two separate integrals. And that's the technique I'm going to use here. I'm going to rewrite this as the integral of 2 over the square root of x squared plus 1 plus, with respect to x, plus the integral of 5x over the square root of x squared plus 1. So I'm just splitting that fraction up into two separate integrals. Now that's a good thing to do because the first integral, if I just take, let me highlight it, this first integral here, if I just take that 2 outside the integral, so let me do that, then we can see that actually, then we can see that this, the 1 over the square root of x squared plus 1, that's one of our standard results we just saw a moment ago. That's going to integrate to be sinh. So that's going to integrate quite nicely, that first term, that first integral. The second integral is a little bit trickier. We've got 5x over the square root of x squared minus 1. But we can actually do that because we can spot a derivative for that. It's not particularly easy to spot, but we can do it because the derivative of what's on the inside down here is 2x, which is similar to what I've got here. So I'm going to rewrite that second integral. So let me just rewrite this whole thing first. Okay, so I'm going to rewrite this as I'm going to take the 5 outside, and I'm going to rewrite this as x times x squared plus 1 to the power of minus 1/2. So all I've done there is I took the 5 outside, and I have moved all of this to be on the numerator, hence why it's a minus power, and the power is obviously 1/2 because it's square root. So this is nearly the derivative of this. I just need an extra 2 at the front. So let's put that 2 in. I'm allowed to do that as long as I take a 2 on the outside there. And now this is the derivative of this, so I can integrate that easily by spotting a derivative. All I need to do is ignore that, ignore this 2x completely, add 1 to the power, and then divide by the new power. So let's complete this integral now. So like I say, this first term will integrate just to be 2 arsinh x. The second integral, we've got 5 over 2 times, we're going to add 1 to the power, so we're going to add 1 to the minus 1/2, so that's now going to become plus 1/2. Divide by the new power, so divide by 1/2 is the same thing as timesing by 2. These cancel out, and we just get left with 2 arsinh x plus 5 lots of x squared plus 1, all square rooted, plus c. So that's an example where we split a fraction up, we used one standard result, and we used the spotting derivative technique from regular A-level maths. Next, we're going to use the technique of spotting a derivative. So, similar to before, but a little bit, could be a little bit more difficult to spot, maybe. So we're going to do 2 examples here. So this first example, I'm going to, just to make this a bit easier for you to spot maybe, let me rewrite this as sinh 2x multiplied by cosh 2x to the power of 5. Hopefully you can see that this, the way I've written this is exactly the same as what they've got there. It just might look a bit more familiar to you. The point is that the derivative of this would be 2 sinh 2x. So I need an extra 2 at the front here, which I can do as long as I have a 1/2 at the front. Now, this is the derivative of the cosh 2x, so I can ignore that completely. I can add 1 to the power, so I'll get cosh 2x to the power 6 now, and then divide by that new power, so divide by 6. And there we go. Next we have the tanh x. Now I can think of tanh as being sinh over cosh. And that's a good thing because sinh is the derivative of cosh. So I have an integral in the form of f dash of x over f of x, which we know that we can do with a logarithm. So this is going to integrate to be ln of cosh x plus c. I put the modulus there just to be careful, but we know that cosh is always going to be positive, so technically I don't really need, oopsie daisy. Technically I don't really need the modulus sign there. I could have just written ln Cosh. So that's a couple more examples where we have used the techniques of spotting a derivative. We're going to do three more examples in this video. So here we're going to be using some hyperbolic identities to help us to integrate these. So let's focus on that first one. We've got Cosh squared 3x. Now remember how we integrated cos squared or sine squared in regular A-level maths with the trigonometric functions. Whenever you needed to integrate either cos squared or sine squared, we use the cos double angle formula to do so. And so therefore we're going to use a similar technique here. If I want to integrate Cosh squared, I'm going to use the Cosh double angle formula. So the Cosh double angle formula, remember, from the, I think, the third video of this series, Cosh 2x is equal to 2 Cosh squared x minus 1. So I can then rearrange this to make Cosh squared the subject. So I will have Cosh squared x is equal to Cosh 2x plus 1 all divided by 2. Excuse me. But obviously here I've got a 3x on the inside here, not an x. So I need this to be 3x. So I'll have Cosh squared 3x would be equal to Cosh. So this is now going to be 6x. If I make this 3 times bigger, then this is going to get 3 times bigger as well and become 6x plus 1 all over 2. We can now integrate that. So instead of integrating the Cosh squared 3x, we're going to integrate Cosh 6x plus 1 all over 2. But to make my life easier, I'm going to take that half outside. I know that Cosh integrates to be sinh, but because of the 6x on the inside there, I need to divide by 6. Plus the 1 is going to divide by, is going to integrate to be x. And don't forget, obviously, the half we had at the front there. So that's going to simplify to be 1/12 oops, bear with me. Okay, so that's going to simplify to be 1/12 sinh 6x plus half x plus c. And then that's that first one done. Right, the second one, we've got sinh cubed x. Now, I'm going to show you a technique that we could use for, actually, we could do this for all odd powers. This technique I'm going to show you. It's not just for cubed. We could do it for power 5. We don't want to do it for too high powers because it will be quite confusing or quite long in those other techniques. So you would need a longer different technique if the power was high. But if it's sinh cubed or sinh to the power 5, if it's Cosh cubed or Cosh to the power 5, this is the technique that we would use. We're going to rewrite that sinh cubed as sinh squared times sinh. We know that's the same thing as sinh cubed. Now I'm going to use the hyperbolic identity that I know that sinh squared is the same thing as Cosh squared minus 1. I'm now going to expand the brackets. So I'll get sinh times Cosh squared minus sinh. Now you might think, oh my goodness, you've taken something that was nice and simple and made it much harder. And I've made it much longer, but I've made it much easier to integrate. Because first of all, the cinch is going to integrate to Cosh really nicely. And notice over here we have our good friend of spotting a derivative. The inside here is Cosh, and that differentiates to be cinch. So that allows me to ignore the outside completely, raise the power, so I'll get Cosh cubed, divide by the new power, 1/3. Integrate cinch and I get Cosh. Don't forget your plus c. And we're done. That is the integral of cinch cubed. Like I said, you could use the same technique for Cosh cubed as well. Okay, last example in this video is where we have exponentials involved. So here I want the integral of e to the power 2x times cinch x. Now, because we have an exponential involved, it would make sense to actually rewrite cinch in its exponential form. Notice I haven't actually done this in any of the previous examples. I haven't written cinch as e to the power x minus e to the power minus x over 2, but we know we can do that, and it would make sense to do that because we have this e to the power x 2x there as well. I will then take the half outside the integral, and while I'm at it, I'm going to expand these brackets as well. So I'm going to have the e to the power 2x times e to the power x. So that's going to be e to the power 3x. E to the power 2x times e to the power minus x will be e to the power x. And now both of these integrate nice and easily. E to the power 3x will integrate to be e to the power 3x divided by 3. E to the power x will integrate to be e to the power x. And so we will get our answer as 1/6 e to the power 3x minus 1/2 e to the power x plus c. And we're done. So let me just summarise those techniques that we've seen in this video. If you have exponentials involved, then use the exponential form of the hyperbolic function. If we have a cinch cubed or a Cosh cubed, then split it up into cinch squared times cinch, and then use the identities to rewrite the cinch squared so that you can spot a derivative. Cosh squared, use the double angle formula. Cinch squared, use the double angle formula. Our good old friend spotting the derivative and splitting a fraction up into two parts so that you can use those standard results that are given to you on the formula booklet.